This video is on Chapter 2, Section 2.6, Video Streaming and Content Distribution Networks, CDNs. A major use of network bandwidth is for video traffic. A study in 2015 showed that Netflix, with about 75 million members, used 37%, and YouTube, with about 1 billion users, took 16% of downstream residential traffic. That's more than half of the residential ISP traffic. How do you scale to reach all those users which continue to grow? The technology simply involves storing video on a server that is provided upon request from a client. A straightforward way to provide streaming video is to build a single massive data center with servers that hold all its videos in the data center and to stream the videos directly from the data center to customers worldwide. But that approach won't work for a number of reasons. You can pause the video and think for a moment about the problems there and why that wouldn't work well. First, a problem with this approach is that a single mega video server data center would mean a single point of failure. If something goes wrong with the data center or its links to the internet, you would have no service available. Second, similar to the previous discussion on cache, a popular video could have a huge number of requests, and then the video would be sent many times over the same communication links, which is inefficient, a waste of bandwidth, resulting in congested links, or paying up huge costs for additional bandwidth. Any reasonable solution would be to distribute video servers at key locations and not concentrate them into one single mega video server in one spot. The major challenge of a single mega video server is heterogeneity. Different users have different capabilities. Some have higher bandwidth, some have poor bandwidth. The end device could be a mobile user to someone with a laptop on Wi-Fi to someone with a wired internet to a smart TV. Furthermore, if the client is far from the data center, the packets on the server to the client will cross many communication links, and even possibly through different ISPs, and if worldwide, with ISPs located in different continents. Obviously, there will be different capacities, and if any link provides less than video playback rate, the end-to-end throughput will be below the video consumption rate, which will result in freezing and annoying delays for the user. The likelihood of this happening increases as the number of links in the end-to-end path increases. So the solution has to be a distributed infrastructure at the application level, a content distribution network. Before we go into the details of the best way to provide video streaming, let's look at how video works. A video is a sequence of images displayed at a constant rate, for example, at 24 or 30 images per second. A digitally encoded image consists of an array of pixels, with each pixel encoded into a number of bits to represent luminance and color. The number of bits within and between the images can be reduced. With spatial coding within an image, where if there is, for example, a lot of purple in the image, instead of repeating the purple value, just the purple value and the number of repeated purple pixels is used. Temporal coding from one image to the next uses one frame, and the next frame just lists the differences from the previous frame. There are two video encoding rates. With CBR, constant bit rate, the video encoding rate is fixed. VBR, variable bit rate, the video encoding rate changes as the amount of spatial and temporal coding changes. Some examples are MPEG-1 for CD-ROM is 1.5 megabits per second, MPEG-2 for DVD at 3.6 megabits per second, and MPEG-4, often used in the internet, is less than 1 megabit per second. Video can be compressed to create multiple versions of the same video with different bit rates, trading lower video quality for a lower bit rate. Compression can be used to create, for example, 3 versions of the same video at rates of 300 kilobits per second, 1 megabit per second, and 3 megabits per second. Which version to use is based on the current available bandwidth. For high-speed internet connections, users can use the 3 megabits per second version. The 300 kilobit per second version is useful for users watching a video over 3G with a smartphone. So here is a basic scenario for streaming a stored video using HTTP. Videos are stored at an HTTP server on an ordinary file with a specific URL. When a user wants to see the video, the client establishes a TCP connection with the server and issues an HTTP GET request for that URL. The server then sends the video file within an HTTP response message. On the client side, the bytes are collected in a client application buffer, and when the amount of the bytes exceed a specific threshold, the streaming video application takes the video frames from the client application buffer and displays them on the user screen. While streaming using HTTP has been used extensively, for example by YouTube, it has a major shortcoming. Despite the large variations in the amount of bandwidth available to clients, all clients receive the same encoding of the video. As a result of this limitation, DASH was developed. DASH stands for Dynamic Adaptive Streaming over HTTP and is a new type of HTTP-based streaming. On the server, a video is divided into multiple chunks, and each chunk is encoded at a different rate with a different quality level. A manifest file has the URL for the different chunks. The client measures the server-to-client bandwidth and uses it to get the URL from the manifest for the chunk with the coding rate matching the current bandwidth. Depending on the bandwidth, the client can select different coding rates based on the bandwidth available. With a higher bandwidth, a higher rate version provides higher quality. With a lower bandwidth, a lower rate with lower quality has to be used. Hence, DASH allows the client to adapt to the available bandwidth if the available end-to-end bandwidth changes during the session. At the beginning of this section, I mentioned the challenge of scalability and being able to stream to hundreds of thousands or more of simultaneous users. We had mentioned the problems using a single mega server from being a single point of failure, sending many copies of a video into the network, causing network congestion, and long distances to clients, and having to go through different connectivity links and equipment with different capabilities will result in bottlenecks. The bottom line, it doesn't scale. Instead of a single location, distribute the location of video servers on multiple geographic areas nearer the edge to get close to end users, reducing the number of links and routers between the end user and the CDN server. This is called enter deep, deploying server clusters into access ISP networks that are close to users. The highly distributed design has the task and cost of maintaining and managing the clusters. This is the design philosophy used by Akamai with 1,700 locations. A second design philosophy used by Limelight and many other CDN companies is called bring the ISPs home, and is in building large clusters at a smaller number, for example, tens of sites. Instead of inside the access ISPs, these CDN clusters are at internet exchange points. The bring home design has less maintenance and management overhead than the enter deep design philosophy. But compared to the enter deep design, it gives up fewer delay and higher throughput to the end user. Once its clusters are in place, the CDN replicates content across its clusters. When a subscriber requests content from CDN, it is directed to a nearby copy and gets the content from there. Note if the network path is congested, the subscriber may choose a different copy. Some challenges are how to determine which CDN to get content, how to cope when the internet is congested, what happens with viewers when there is congestion, and what content to place on which node. For example, the CDN may not want to place a copy of every video in each cluster, as some videos are rarely requested or are unique in popularity only to certain countries. CDNs deploy DNSs to determine which CDN to get content from which we will see in the next slide. CDNs take advantage of DNS to intercept and redirect requests. To see how, let's look at this example to show how DNS is used. NetCinema, a content provider that has videos, stores this video at King CDN to distribute its videos to its customers. Each video has a unique identifier that is part of the URL to identify the video. For example, let's call it 6Y7B23V. Step 1. Bob visits the video page at NetCinema, and he gets the URL for the movie. When Bob clicks on the link http:/video.netcinema.com 6Y7B23V, Bob's host sends a DNS query for video.netcinema.com. Bob's local DNS server, LDNS, relays the DNS query to an authoritative DNS server for NetCinema. which sees the unique identifier after the host name, video.netcinema.com. They hand over the DNS query to King CDN. Instead of returning an IP address, the NetCinema authoritative DNS server replies to the local DNS server with a host name in the King CDN domain. For example, at A1105, kingcdn.com. Now, any DNS query on Bob's local DNS server will use the King CDN's private DNS infrastructure. When Bob's LDNS sends a second query, now for A1105.kingcdn.com, the King CDN's DNS system returns the IP address of a King CDN content server to the LDNS, and the client will receive its content from the King CDN's content server. This textbook provides a case study of 3 highly successful large-scale deployments of streaming stored video. We're all familiar with Netflix and YouTube, and there's a third company called CanCan. The case studies show each of their different approaches and are good examples of using the underlying principles that have been discussed in this section. I'll leave these for you to read for yourself. This concludes the video on Section 2.6, Video Streaming Content Distribution Networks.